Example 5.2. A spherical surface of radius r has charge uniformly distributed over its surface with a density of q divided by 4 pi r squared, except for a spherical cap at the north pole, defined by the cone theta equals alpha. What is the potential inside? Outside? B. What is the magnitude and direction of the electric field at the origin? C. Discuss the limiting forms of the potential and electric field as the spherical cap becomes very small or very large. Using the axis of the cone as the vertical z-axis, we clearly have azimuthal symmetry. We also have azimuthal symmetry for a ring charge. For a ring of charge at the boundary of the cone, for example, we have C the equation,
where r sub is less than, r sub is greater than, are the values C, r, according to which is smaller, where r is the radial coordinate of the potential and C is the radial coordinate of the charged ring. Let's consider rings of charge of width r d theta prime at angle theta prime such that the ring circumference is 2 pi r the sine of theta prime. We then get for the charged ring. See the equation shown. Let's integrate the charged rings from cone edge at angle theta equals alpha to the maximum at theta equals pi. See the equation. Using the relation see the equation shown, we get, see the equation. For L equals 0, the integral from -1 to cosine alpha of p sub L of x dx equals p sub 1, the cosine of alpha, positive 1. Thus,
see the equation shown. For r is greater than r, simply switch the fraction with numerator r to the LTH power and denominator r raised to the L plus 1 power goes to the fraction with numerator r to the LTH power and denominator r raised to the L plus 1 power. B. Let's now consider the electric field. Recall that E equals negative gradient phi implies that see the equation. Since the latter expression isn't well defined at precisely the place of interest, r equals 0, we must approach the value r equals 0 with care. Let's consider an expansion in small r. The main contribution to phi at first order in r is then, see the equation shown. Evaluating the derivatives, we get
the partial derivative of phi with respect to r equals q over 12, 3 the cosine squared of alpha minus 3, the fraction with numerator cosine theta and denominator r squared, and the partial derivative of phi with respect to theta equals q over 12, 3 the cosine squared of alpha plus 1, the fraction with numerator, negative the sine of theta, and denominator r squared times r. The field is thus, see the equation. C. Consider alpha goes to 0, redoing the expression from a, separating the L equals 0 and L greater than 0 terms. First consider for L equals 0, see the equation shown. Thus, see the equation. Notice that the result is the potential of a uniform spherical shell with total charge Q minus that of a point charge located at Z equals plus R.
For the E field at R equals 0 as alpha goes to 0, see the equation shown. Example 5.3. A thin, flat, conducting circular disk of radius r is located in the xy plane with its center at the origin, and it is maintained at a fixed potential V. The charge density on the disk is proportional to r squared minus rho squared, raised to the exponent -1 divided by 2 end exponent, where rho is the radial distance on the disk. A. Find the potential for r greater than r. B. Find the potential for r less than r. C. Find the capacitance of the disk. Solution. Once again, we make use of the result for the potential due to a ring of charge. See the equation. As before, the ring radius and the observer radial distance are first ordered, and the smaller is r sub is less than and the larger is r sub is greater than. Let's first get the total charge, eventually needed for Q equals CV anyway.
Suppose the surface charge density is C, the equation shown, with total charge Q then determining the value of the constant, A, see the equation. So we have dq equals the fraction with numerator q divided by 2 pi and denominator the square root of r squared minus rho squared times 2 pi rho times d rho, and alpha equals pi over 2 goes to cosine alpha equals 0, p sub l, the cosine of alpha, equals 0 for all odd l's. We also have that p sub 2n of 0 equals the fraction with numerator, -1, to the nth power and denominator 2 raised to the 2n power, the fraction with numerator 2n factorial and denominator n factorial. Let's start with the case where r sub is less than equals rho, r sub is greater than equals r.
See the equation shown. We know that lim over r goes to r of phi of r theta equals pi divided by 2 equals v, and for theta equals pi divided by 2 the cosine of theta equals 0 we have the relation. See the equation. Thus, see the equation shown. For r equals r, the inverse sine of 1 equals pi over 2, and we have, see the equation. So, the solution for r is greater than or equal to r is,
see the equation shown. B. To find the potential for r is less than r, let's start from the solution in A, for r is greater than r. Let's consider the behavior when crossing from theta equals 0 with r is greater than r to r is less than r. Start by summing series for theta equals 0 goes to p sub 2l, the cosine of theta, equals 1, see the equation. Notice that the sum form of the Legendre polynomial diverges for r is less than r while the inverse tangent does not. This allows us to uniquely continue the functional dependence according to the inverse tangent of r over r, for r is less than r along the theta equals 0 z-axis. Let's now do an expansion of the inverse tangent form of the potential for r is less than r, theta equals 0, that is valid in that domain, particularly when r equals 0.
See the equation shown, which, when rewritten in terms of matching Legendre expansion, uniquely arrives at the solution for 0 is less than or equal to theta is less than or equal to pi divided by 2. Recall we crossed at theta equals 0, so derivation tied to region above xy plane. See the equation. Now, symmetry above and below the disk implies that phi is even, but since p sub 2l plus 1 is odd, we must have for the potential below the xy axis. See the equation shown. C. For capacitance we have the definition Q equals CV, and recall V equals pi Q divided by 2. Thus, C equals 2 divided by pi. Example 5.4. The surface of a hollow conducting sphere of inner radius, A, is divided into an event number longitudinal orange slices, where the segments alternate in potential according to plus or minus V. A. For 2 n segments, what is the potential inside? B. For case n equals 1, 2 hemispheres. Get terms up to L equals 3. Show agreement with prior results.
Solution A. We no longer have azimuthal symmetry, so general spherical harmonics are needed. See the equation. The potential can't be singular at the origin, without a source there, mean value theorem, thus B sub Lm equals 0 and we have, see the equation shown. Where we can determine the coefficients from, see the equation. Again asserting the mean value theorem, phi of r equals 0 equals A sub 0 0. If n, the number of dividing planes, is odd, phi is odd, y sub Lm is odd, thus only odd L is allowed. Similarly, if n is even, only even L are allowed. Also note that phi of r theta phi equals phi of r pi minus theta phi, which indicates that phi is an even function of cosine theta. Y sub Lm of theta phi is an even function of cosine theta only if p sub L to the nth power of x is an even function of x. The parity of p sub L to the mth power of x is -1 raised to the L plus m power, so L plus m equals even. So if n is even, so are L and m, and if n is odd, so are L and m.
Also note that since phi is a periodic function in phi with 2 pi divided by n, we have a relation imposed on m such that m equals 0 plus or minus n, plus or minus 2n, plus or minus 3n, ... and there is also the relation m divided by n is an integer. Consider one of the dividing planes to be the xz plane, such that see the equation shown. We then alternate, see the equation, then, see the equation shown, etc. Recall the integral with spherical harmonics can be rewritten in terms of the modified Legendre polynomials. See the equation. Let's focus on the phi integral first. See the equation shown. Thus,
see the following equations. B. Consider n equals 1, then L is odd and m equals plus or minus 1, plus or minus 3, plus or minus 5. See the equation. Phi is real, thus y sub L sub 1 minus m equals -1. To the mth power times y sub L sub 1 minus m conjugate goes to A sub L sub 1 minus m equals -1. To the mth power times A sub L minus m conjugate. And we have A sub 1 equals -4 inv over m, the integral from 0 to pi of sine theta of d theta of negative the square root of 3 over 8 pi sine theta, equals 4ib the square root of 3 over 8 pi. The integral from 0 to pi of sine squared theta of d theta equals ib the square root of 3 pi over 2, a sub 1, negative 1 equals, a sub 1. 1 raised to the asterisk power equals ib the square root of 3 pi over 2 and
see the equation shown, and see the equation. So, to order L equals 3 we have, see the following equations.